Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 15 on differentials.
We begin this lecture with a question. What is dx? You may have been waiting your whole life to find out, but you're not going to get a complete answer right now. Sorry. But along the way, we'll learn enough about differentials to be able to answer some important questions about geometry, physics, and economics.
So, what exactly do we mean when we write dx or du? They're used all the time in calculus class. One perspective is that they're infinitesimals, really small bits of x or u, so that when you integrate du, what you get is u. That's a reasonable intuition, but is that really what they mean? Maybe they connote a rate of change, so that, according to the chain rule, du and dx are related by du dx, meaning that if du connotes the rate of change of u and dx the rate of change of x, then they are related by du dx, the rate of change of u with respect to x. That's a reasonable interpretation. It's not the full truth. The full truth is that these are differential forms. We are not, however, going to cover that in this single variable course. For now, let's think about what d is doing. D is an operator, which means that if you put in a function, f, you get out df, this differential that is telling you something about rates of change of outputs with respect to inputs. Now, the fact that it's an operator means that we can differentiate an equation, something of the form f equals g. And what we will get out is, again, an equation, df equals dg. Now, you've probably seen this before. It goes under the name of implicit differentiation, and it's extremely useful. For example, if we want to know the slope of the tangent line to a circle of radius r centered at the origin in the xy plane, then what would we do? We would write down the equation of that circle, x squared plus y squared equals r squared, and then we would differentiate the entire equation. Applying the d operator gives us what? D of x squared is 2x dx. D of y squared is 2y dy. What is d of r squared? Well, if r is a constant, then dr would be equal to 0, or if you like, differentiating a constant gives you 0. This equation, then, involving the differentials dx and dy, allows us to solve for the slope of the tangent line, dy dx. Using a little bit of algebra, we get that it is negative x over y, a result that you can clearly see. Let's turn to an application in economics, this one dealing with substitution rates. In economics, the marginal rate of substitution of a product x for a product y is the rate at which a consumer is willing to exchange the good or product y for the good x. This assumes a fixed utility. I don't want to go too much into economics here, but let's take a moment and explain what this means. This marginal rate of substitution, MRS, can be expressed as minus dy over dx along a curve of fixed utility, u. So let's say we're looking at the xy plane. I have some utility function, u. When we set that equal to a constant, it gives us a curve in the xy plane. The marginal rate of substitution is related to dy dx, the slope of the tangent line. Let's make this a little more specific. Let's say that x is the amount of coffee I have, y the amount of donuts that I have, and my utility function, u, is y squared times quantity, x minus 3. In this case, differentiating that equation gives me du equals d of quantity y squared times x minus 3. Now, since I'm along a fixed utility curve, u is a constant, so du is 0. And on the right, applying the product rule, I get 2y dy times x minus 3 plus y squared times dx. And now, solving for the marginal rate of substitution, that is minus dy over dx, gives me negative y squared over 2y times quantity x minus 3. We can simplify, removing the negative signs and the y's, and we get a marginal rate of substitution of y over 2 times quantity x minus 3. Now, what does that actually mean? What that actually means is that depending on my values of x and y, how much coffee I have versus how many donuts I have, my willingness to trade one for the other changes. If I have an equal amount of coffee and donuts, then that's one thing. I might be willing to trade one for another. However, if the amount of coffee that I have is sufficiently low, that is, x is close to 3, it doesn't matter how many donuts you're willing to give me. I'm not going to give up any more coffee. Differentials often arise in related rates problems. Here's a fun one. Let's say that you have water flowing from a faucet in a smooth stream. What I'd like to know is, how does the cross-sectional shape change? It seems as though the stream gets thinner as you go. Let's assume that the cross-sectional shape is circular. We'll try to see what happens to the radius of that circle. We'll start from the assumption that we have a steady stream, which means that the flow rate through a cross-section must be constant. What is the flow rate? Well, that's the area times the velocity at that slice. If that's a constant, then we can write that equation as pi r squared v equals c, where r is the radius and v is the velocity. Differentiating this equation yields what? Well, we're going to ignore the pi, absorb that into the constant on the right, and then, using the product rule, we get 2r dr times v plus r squared times dv equals 0. Now we can do a little bit of algebra to get our hands on dr. That is negative r squared over 2rv times dv. We can simplify that, canceling the r's, to negative r over 2v dv. And now, let's say we wanted to know how that radius is changing with respect to time. The time rate of change would be dr dt, which we can write as negative r over 2v times dv dt. What can we say now to simplify things? Well, since dv dt is a constant, since the water is falling under the influence of gravity, dv dt is exactly g. And so we get dr dt equals negative r times g over 2v. We could simplify that, knowing what we know about v, to negative r times g over 2 quantity v naught plus g times t, where v naught is the initial velocity coming out of the faucet. That still doesn't tell us exactly what the shape is, say, as a function of height, but we could either solve that differential equation or use some conservation properties from physics to get that shape if we wanted. We have manipulated the differentials to give us information about time rates of change.